drift velocity. In case of conductors, the free electrons are responsible for electric current. Metals contains large number of free electrons. These free electrons are always in continuous random motion. This random motion of free electrons is due to thermal energy. That thermal energy is equal to 3/2 kT, where K is the Boltzmann's constant, T is the absolute temperature. For example, at a day, the room temperature is taken as 30 degrees centigrade. In that room, a conductor is placed. This 30 degrees centigrade converts into absolute scale of temperature, that is 273 plus 30 degrees, which is approximately 303 Kelvin. So, due to this temperature, the free electrons inside the metal contains thermal energy. This thermal energy is responsible for random motion of the free electrons. Random motion of electrons in a conductor. Due to random motion, the free electrons collides with positive metal ions at high frequency. Observe here, these are the random motion. Due to that random motion, they collide with positive ions and undergoes change in direction at each collision. The length of the conductor is A. Once you apply the potential difference across the ends of the conductor, there is an electric field E bar is existed. Electric current is due to flow of free electrons in a conductor. How does the electrons move in a conductor in the absence of electric field? If no electric field is applied, the electrons move randomly in all directions. At any temperature, the free electrons are randomly moving in all possible directions. How does the net rate of flow of electrons at any point in a conductor in the absence of electric field move? That means here what happens, through the reference portion, the number of free electrons flowing from left to right and right to left both are equal. The net flow becomes 0. The rate of flow of electrons from left to right at a point is equal to rate of flow of electrons from right to left. So that the net rate of flow of electrons at that reference point is 0. This is all in the absence of external electric field. Now, how do the electron accelerate in a conductor in the presence of electric field? If no electric field is applied, the net rate of flow of electrons is 0, means the average velocity of these electrons is 0. But now we are going to apply some electric field. In the presence of this electric field, how do the electrons accelerate in a conductor? For that, what do you mean by drift velocity of electrons? So, now the concept is drift velocity. An electric field is set up at every point in the conductor when it is connected by a battery. This field exerts a force on the electrons. Force is acting means, according to Newton's second law, F equal to ma. Force is acting on the free electrons due to applied electric field while the conductor ends connected to a battery. Due to that force, before the application of electric field, the average velocity of all free electrons in a conductor is 0. Now, after applying electric field, they acquire a constant speed in a direction opposite to the field. This constant speed is called the drift velocity. The drift velocity is of the order of 10⁻³ meter per second. Thus, there is a net flow of charge inside the conductor. This is all occur when we apply some external electric field. How do we apply an electric field? By connecting conductor to a battery. So, here the collision between the electron and the atoms and ions are inelastic collision. Inelastic collision means there is net transfer of energy. The average time interval between two successive collisions is called time of relaxation. That time of relaxation is tau. Then drift velocity. To calculate drift velocity, we use dynamic equation. V is equal to U plus AT. What is U here? Initial velocity. Already I told the average velocity in the absence of electric field is 0. Hence, U is equal to 0. What is A? Acceleration. Acceleration when we apply some external electric field. A equal to F by M. This acceleration is caused due to electric field. From electric field intensity definition, E equal to F by Q, which is equal to F by Q is what? Charged particle charge. Here electron is the charge, its charge is E. Then A equal to, instead of F, capital E, small e. Capital E, small e by M. This is acceleration. Initial velocity is 0. During the time of relaxation, what is time of relaxation? The average time interval between two successive collisions, that is tau. T equal to tau, time of relaxation. All these values substitute in V equal to U plus AT, then we get drift velocity Vd equal to minus small e capital E by M into tau. What this negative sign indicates? Here the negative sign indicates that the electrons drift opposite to the applied electric field. Why? Because like that. Because this is the conductor whose one end is connected to battery positive terminal, second end is connected to battery negative terminal. Now, the free electrons are negatively charged particles. These free electrons, attracted by the positive end, they travel along this direction. Means these free electrons drift opposite to the applied electric field. What is the direction of the electric field? The electric field is always from positive to negative along this direction. This is the electric field direction. What is the motion of the electric electrons? The motion of the electrons directed from negative to positive terminal. That means the electrons are drift opposite to the applied electric field. This is indicated by the negative sign. Now points to remember. When electrons are drifted in a conductor, they will have net average velocity and zero average acceleration. Why zero average net acceleration? Because the drift velocity is a constant velocity. Hence, the average acceleration becomes 0. In the absence of external electric field, there will be no current. Why? Because the net rate of flow becomes 0. Number of charge carriers means electrons moving from left to right and right to left at a point are same. Hence, the net rate of flow becomes 0. That implies no current in the conductor in the absence of external electric field. Now, electric current density represented with J. What is this electric current density? Current density is defined as the current per unit area. J is I by A, taken normal to the current I by A, and the current density is denoted by J. The magnitude of current density is the amount of charge flowing per unit cross section area per second. That we called current density. Current density is a vector quantity. Current is a scalar quantity. But current density is a vector quantity. If capital E is the magnitude of uniform electric field in a conductor whose length is L and potential difference V, the relation between electric field intensity and potential, that is V equal to ED. The potential difference V is equal to ED. E is the electric field intensity. Here D is length of the conductor, that is L. Means applied potential difference V equal to E into L. Now, the potential difference is equal to EL, which is equal to current density into rho into L. Here, L gets cancelled. Then, E is equal to J rho. From there, the above relation for the magnitude of electric field intensity and J is current density. The relation between the two is given by this expression, that is E equal to J rho, where equal to J rho. The current density, which we have defined as the current through unit area and normal to the current. It also directed along electric field direction. Means the direction of current density is also along the direction of electric field intensity, where J is equal to E by rho. Rho is the resistivity. 1 by rho, reciprocal of resistivity is conductivity. Hence, the conductivity is sigma, then current density J equal to sigma into E, where sigma is 1 by rho. Rho is the resistivity, reciprocal of resistivity is conductivity. So, this is the relation between current density, conductivity and electric field intensity. What is that relation? J equal to sigma E. The current density SI unit is, current density J is I by A. I ampere, measured in amperes, area meter square, ampere per meter square is the SI unit of current density. And dimensional formula is, current is a fundamental quantity. The dimensional formula of current is capital I, area L square. That means current by area I by L square. That L square goes to top as L power minus 2. So I L power minus 2.